situation where your route can be complex. In such cases, we need some special technique to proceed with. Actually, when we supplied you with a course plan, okay, in this week we have to proceed in such a way that we can be adhering with the plan that we made, but unfortunately we are a bit lagging behind because of Ramadan. For this reason, I am leaving the two techniques to be explored later. This is there in your chapter 7, article 7.4 and 7.5. The method has the basic principle that is with you from your very elementary level. Okay, you can have a look there. We'll be going into it later after having something discussed, probably in the next week, inshallah. So today we'll be going to chapter 9, okay, finding the solutions of linear algebraic equations. You are dealing with this thing from very earlier level. If we have a system of equations that are connected by some simultaneous equations, then we can solve them by using some techniques. Okay, in your earlier level, you started with two variables. Then we increased the number of variables. Then we explored how the system of equations can be solved. They can be solved in many different ways. Either you can solve them graphically, or you can solve them by using some technique we call matrix inversion or Cramer's rule. Have you heard about Cramer's rule earlier?
Yes, sir.
Okay, thank you. Where you used it?
Sir,
In
while
engineering
solving the
problem,
linear
did you
equations.
find any applications of Cramer's rule?
Sir, while solving linear equations.
While solving linear equation, yes, but the technique is what? Is it not a technique that is very similar to finding the determinant?
Yes, sir.
Isn't it? We will have a solution for a particular variable that will be equal to a numerator denominator. That numerator denominator is constructed by the coefficient denominator by replacing the corresponding column by using the constant column, isn't it? Then you will have a denominator and determinant that is equal to the determinant of the coefficient matrix. So in this way, we apply Cramer's rule, you know this thing. Another technique can be a matrix inversion type, okay? That means we can express our linear system equations into a form of matrix. Then you can apply your matrix algebra there to find the inverse. Then we can find the solution, okay? Or if your variables are a few numbers of variables are there, a graphical technique can also be employed there to find the solution, isn't it? In your intermediate level or even in some earlier levels, didn't you find the solution of two variable problem? For example, okay, usually what we can do, if we have a system of equation, this system of equation is can be written, for example, in the general form. It is there in equation 9.1. This equation can also be written in the matrix form, something like this. Matrix A multiplied by matrix X is equal to matrix B. Can we write this? Where A is a square matrix is the number of unknown is equal to the number of what? Your equation, then the coefficient matrix will be equal to what? Would it not be A matrix will be a square matrix? Is it? If
Yes.
the number of equations equal to the number of unknowns, then coefficient matrix A would be equal to what? Is it not a square matrix?
Yes, sir.
Yes.
Then your A will be equal to what? A column matrix, x1 through xn. And your B will also be a column matrix from B1 to Bn. Then by using matrix inversion technique, X is equal to what? Is it not equal to A inverse multiplied by B?
Yes, sir.
So in this way you can do, or what you can do, you can use your Cramer's rule to find X1. Your X1 would be equal to a determinant there. And this is what the determinant of A. And that determinant of A is equal to, you replace this column by B1, B2 to Bn, and all other coefficient will be remaining same. In this way, you can do that. But all these techniques is actually, Cramer's rule can be applicable only when this determinant will be calculatable or manageable. Otherwise, you cannot do that. So why I'm telling this thing, we'll be just discussing a bit later, okay? That what is the problem with A? Because sometimes you see that A can have zero value. Okay, when your A value is zero, that means determinant of A equal to zero. Can you proceed with Cramer's rule? A determinant zero, can we do that? Can we use your Cramer's rule?
No, sir.
Then I will, this is very elementary technique. I will not discuss this thing that much. You see that the equations for, you can use your graphical technique. If you have two equations there, for example, say 1x1 plus A, something like this, then what you can do, you rearrange the equation in the form of a straight line, then you plot them in the XY plane, then you will see that these two straight line will intersect at a particular point. That point is the solution, isn't it?
Yes, sir.
But this technique is only applicable. You see that your equation will have a slope. First equation will have a slope equal to what? First equation will have a slope. That slope is equal to, if we solve for x2, for example, say in the case, it is something like this. Y is equal to mx plus c. You form this equation. Here your x is equal to say x1 and your y is equal to say x2. In this case, your slope of equation 1 would be equal to what? Minus a11 divided by a12. Your slope of your second equation will be equal to what? Minus a21 divided by a22, isn't it? Then if these two equations, this is your x1, this is your x2, if these two equations, for example, coincide at this point, intersect at this point, then this is the solution for your x1 and x2. But that can sometimes will create some problem. Actually, this quantity, if we want to calculate this quantity by, okay, if you want to solve this thing by using Cramer's rule, then your x1 equal to what? Your x1 equal to determinant b1, b2 into a1 to a22 divided by a11, a12, a21, a22, isn't it? Then this determinant say equal to del. That delta equal to what? A11 into a12 minus a21 into a22. Are not this thing is related to these two factors? For example, if these two slopes are nearly equal, that means a11 divided by a12 is nearly equal to a21 divided by a22. Then this multiplication a11 into a22 minus a12 into a21, this is nearly equal to 0, isn't it?
Yes, sir.
This 0 is actually is nothing but this is the value of your determinant delta. Thus, that means if your delta value is nearly equal to 0, what does it mean? It means that the slope of these two equations are nearly equal. Even when they are exactly equal to 0, what will happen then? The slopes are exactly equal, isn't it? So when the slope of two lines are exactly equal, are not they parallel?
Yes, sir.
If they are parallel, will you obtain any intersection between them?
No, sir.
Will there be any solution?
No, sir.
No solution will be there for equation with parallel lines, okay? But your equation can have same intercept and same slope. In this case, what will happen? You will be obtaining, for example, figure 9.2b. You see that the intercept and slope of these two equations are same. As a result, one equation overlaps other. How many solutions are there? In the first case, no solution. In the second case, infinite numbers of solutions are there. In the third case, you see that although your slopes are not equal, but they are very close to each other. As a result, a extended region will be there where an overlap could be there. So what will happen then if you have a situation there? Then a small variation of the coefficient A1 or any of the coefficient there present will just make a drastic change in the solution. Okay, that means you can have a solution there, you can have a solution there, but to be very precise, there will be only one intersecting point. So in order to find that point, intersecting point, we'll have some problem. Okay, this type of problem is called yield post type problem, yield post or yield condition problem, ILL yield post or yield condition problem. The yield condition problem has some standard technique to handle them. But if you have your numbers of equation increasing, actually, in this case, even your Cramer's rule, hand calculation is very time consuming and in some cases very complicated. But in computer implementation, it may not be that complicated if it satisfies the other conditions. Like your determinant should have a finite value, or it must not be singular. But if we have our equations very few in number, then we can solve the equations by using our hand calculator. So apart from the direct method of solution of your simultaneous equation, we have some other techniques that is a bit systematic and have some advantages. We can discuss about them. And I hope you have some introduction about this thing earlier. We call the technique elimination type. Have you heard about elimination technique earlier?
Yes, sir.
So in your linear algebra courses or matrixing courses, you might have some introduction about this process elimination technique. The process elimination techniques has some other variant. For this region, the standard classical technique is called Naive-Gauss elimination technique. In this case, if we have a system of equations, we gradually eliminate the variable in such a way that your last equation will have a single variable, and we can then proceed with from the bottom to top or backward substitution to find the solution. The Gauss's elimination technique is very simple to be understood, but it has some problems. We'll be discussing about the. So your equation is 9.1 to 9.c are the simultaneous equation. You have to solve for x1 through xn. In the elimination of unknowns, how to find the elimination? You have to eliminate in such a way so that the coefficient matrix in the left-hand side or the equations in the left-hand side becomes a upper triangular form. That means if we have these equations with us, then we have to write your equation in such a way. So that let us illustrate the thing for a 3 equation system. Say it is 1, 1, x1 plus a1, 2, x2 plus a1, 3, x3 is equal to say b1. Another equation is a2, 1, x1 plus A22 x2, A23 x3 is equal to B2, A31 x1 plus A32 x2 plus A33 x3 is equal to B3. Okay, in the elimination process, what we need to do, we find a factor, say A21 divided by A12, A11, and multiply equation 1. This is equation 1, 2, 3. And multiply equation 1 with this factor. That will result you an equation. That equation equal to what? It will be equal to A21 x1 plus A12 into A21 divided by A11 into x2 plus A31 into A21 divided by A11 into x3 is equal to B1 into A21 divided by A11, isn't it? Then you subtract equation this equation that you are obtaining from equation 2, and that will result of the elimination of x1 from equation 2. So what you can do then, ultimately you will obtain a set of equations something like this: A11 x1 plus A12 x2, A13 x3 is equal to B1. Next equation will be equal to A22 prime x2 plus A23 prime x3 is equal to, say, B2 prime. And after that, third, eliminating the second variable from third equation, you will obtain an equation there: A33 prime is equal to, say, B3 prime. X3 will be there. But you see that you are forming a metric that is similar to upper triangle one. And what you can do then? You can start from the bottom side. Okay. In this case, you see that your x3 would be equal to B3 prime divided by A33 prime. And your x2 can again be determined from new equation 2. Then you use your x3 and x2 to equation 1, you can obtain that equation. This is what the essence of your name Gaussian elimination technique. But this technique has some disadvantages. What are the disadvantages? Number one, as many multiplication, addition, and division will be needed. So it is computationally inefficient. Another issue is that if any one element, we call it pivotal element, if that element is equal to 0, we cannot, or even it is very small, then this method cannot be effectively used. So in such cases, what you can do, if it is if A11 is very, not only A11, the pivotal element that we are used to normalize the other equations is very small or nearly equal to 0, then what we can do, we can rearrange the equations, and that rearrangement can be made by changing a non-zero pivotal value. In such cases, it is called partial pivoting. So either you can pivot in the row wise, or you can pivot in the column wise, or you can go in both. If we go in both, then rearranging both, then you can change. That will not change the solution, but it will increase the effectiveness of the algorithm. That is also discussed there in the subsequent sections. Some examples are there. Okay, all the process has been described. Okay, you can apply this thing there. You know this thing from your earlier level, so I will not be discussing the thing to that much. Okay, this is your Naive-Gauss elimination technique. But two important factors are there as the number of equations are in operation counting. Sometimes we call floating point operations or flops. You see that the number of flops needed for Gaussian elimination technique is in the order of n cube. N is the order of your equation. Okay. So if the number of equations are very huge, more than 100, then huge computational burden will be there in the computer for this region. In most of the cases, this technique is not used. Okay, this is illustrated there. Then pitfalls are there, division by zero that I have already discussed. In this case, you have to rearrange the equations so that a non-zero value can be made a pivot and proceed with elimination. Another issue is the round-up error. Round-up error, you know that each computer has a capability of representing in numbers. So whenever two nearly equal numbers are subtracted, then that subtracted value is rounded up, then a huge error will be in there in terms of significant figures. For this region, some cancellation occurs. This is called catastrophic cancellation or subtractive cancellation. And that roundup will affect the accuracy of the result. How this will affect, this can be illustrated by using an example we'll be dealing with, particularly when we are dealing with the yield conditions problem. This is very prone to those cancellation errors. An example of the yield conditions problem, that yield conditions problems here, we are defining it in such a way that if you have your equations, those equations are, example is a simple equation, okay, that your determinant is nearly equal to zero, or in the case of two equations, you can say that your slopes are nearly equal. Then a minor change in the coefficient will make a drastic change in the solution. This is illustrated by using this example. This is the original form of the equation. Later, you have been asked to solve if x1 coefficient of equation 2, that means 1.1 is changed to 1.05, a minor change is there. Then let us examine how your solution will be affected, okay? The equation is solved as it is. Your solution equal to x1 equal to 4, x2 equal to 3. Now, if we change the coefficient of x1 in equation 2 to from 1.1 to 1.05, you see that your solution is equal to 8 and 1. This solution is completely different from what you have obtained earlier. Although if we just want to verify that their solutions are whether correct or not by substituting them into the original equation and examine whether your equations are satisfied or not, you see that they nearly satisfied, but your solutions are not correct. So this will give you something misleading. For this reason, some other special technique will be needed to handle this situation. This thing I have already discussed, that if your determinant is nearly equal to 0, then we cannot do it. Another issue is that your determinant can be made finite by scaling. Scaling means what? If you multiply by a factor, both sides of the equation by a factor, it will not change the solution of your system, but it will improve the situation of the what we call a near singular determinant. For example, say if we have our set of equations in B, your equations are these, the determinant of B equal to minus 0.2. If we multiply the equation by 10, both equations by 10, you see that your determinant become minus 20. Although the solution will not be changing, okay? But in that scaling will create some sometimes some problem. For this reason, scaling can be done in such a way that the maximum coefficient of your resulting system will be equal to 1. That will also some improvement. You try to revisit example 9.1, you will see that what improvements is made there. Try to read something out. Otherwise, if I want to go on discussing the thing, then it will not be very beneficial to you if you do not engage yourself to some extent. Significant figure actually is one of the ways to circumvent many of our problem that arises from the roundup error. So your pivoting issue is already I have discussed that if you have your singular problem, that means if you have your pivotal element in your original equations nearly equal to 0 or equal to 0, then you cannot proceed with your equation as they are given. what you need to do, you have to change your pivoting technique by rearranging your column or rows. That technique have been discussed there, okay? If we just go through this example, then everything will be clear to you, how your pivoting rearrangement will help you to circumvent the problem of ill post type. For example, say, if we have our equations there, two equations are there, you can easily see that in your first equation, you have your coefficient for x1 that is equal to 0.003 by 0.0003, okay, very small in compared with the other coefficient values. Then if we want to proceed with the solution, you will see that our solution can be equal to x1 equal to 1 by 3. Or exact solution is this. Your solution can be something like, after having elimination done, we are obtaining a solution x2 equal to 2 by 3. That solution is exactly equal to the solution that we obtained from this problem by using other technique. But in your computational algorithm, what you will see that as your computer cannot store number x2 equal to 2 by 3, because it will be stored as a flat floating point number, isn't it? Your 2 by 3 equal to what? Hey, what is the value of 2 by 3?
So 0.6666.
6666666. It will never converge, okay? So what you can do then, we can truncate it after finite numbers of decimal places by rounding up, isn't it? If we use, for example, 3 significant figures, then you will have a result. If you use the significant figures 4, then you will have a result. But if the number of significant figure will drastically affect the solution of the other unknowns that needs this value, then this solution, this technique is not efficient, okay, and it cannot be used. Okay, just this is illustrated by using this thing. So using the naive technique, we obtain a solution x2 equal to 2 by 3. And by using this 2 by 3, we are obtaining x1. X1 equation is this. Now, although we have written the equation 3 into 2 by 3 there, but in computer, it will be never written in this way. It will be multiplied by 3 into the factor x2 with the figures, significant figures that we mentioned. So in this way, you see that how the reason is that you see that if we subtract the numerator, what is the value of 3 into 2 by 3? Is it not equal to 2?
Yes, sir.
If it is 2, then you are subtracting a number equal to 2.400001 minus 2. That means 2 nearly equal number you are subtracting. If we have our significant figure 3 there, then you will see that your result, your numerator would be equal to 0. 0 divided by 0.003 is simply equal to 0. That means in this case, your x1 would be equal to 0. So this is there explained, okay? If we have our significant figures there, then gradually you can proceed with your solution. If you significance 4, in this case, it will be 0. If we have a significant figure 3, then our result is equal to, if that means your 2 divided by 3 would be equal to 0.667. In this case, your x1 result would be equal to minus 3.33. That is far away from your actual result 1 by 3. And your error will be equal to this percentage. If we increase the number of significant figure to 4, then it will be equal to 0. If we use the number of significant figures to, and your 100% error is there. If we use 5, then you see that your results are gradually improving. That means you have to use a huge number of significant figures to obtain your result, correct result. And it is not computationally actually efficient. So what we can do as a remedy, you just rearrange the equation, solve the equations, okay? Or if you have your equation that is more than 2, in such cases, you sort for your row and column with larger value of your coefficient A11, then you can solve this equation there and you proceed with your elimination. So in this simple example, we are swapping equation 2 to 3, 1 to 2 in the and apply our elimination technique there. By using the same technique, your solution is there, x2 equal to 2 by 3, and by using your x2 in equation 1, we are obtaining the solution equal to 1 minus 2 by 3 by 1. And let us examine that how your significant figure will affect the result. You see that our significant figure say 3, and if it is 0.667, then your result x1 will be 0.333. And you see that the error is 0.01. It is much more efficient than what you have observed in your earlier case. And you can easily see that if we increase the number of significant figure, your error is gradually decreasing. It is in terms of percentage. Thus, even we can use our 3 significant figures to obtain a fairly good or accurate result there. Thus, this is how your pivoting strategy will help us to obtain our results that is much more satisfactory than others. This example actually again tells us about your rounding up error. You try to revisit this thing. I hope you will have some understanding about how this thing will happen. Now your computer algorithm is there. You have your computer algorithm already presented in your book. Then you can implement it in your computer to find the solution. Now, how physically we actually apply this thing? If we have a system, then mathematically you will model the system. That system will result you a form of equation. Usually we do this. Usually the steady state type problem of electrical engineering will result you some algebraic type equation. Okay. This can be linear or nonlinear. We will be talking about nonlinear a bit later. But if you have a transient time problem present in the network that contain energy storage element, then differential equation can be involved there. But if you have a simple what you call resistive type network, then your equation will be simple algebraic type. Have you applied your Cramer's rule or matrix inversion in your electrical engineering courses earlier? Not in mathematics. I am telling you that whether you are using this thing to your electrical engineering problems or not.
Yes, sir, in AC circuits.
Not only in AC circuit, didn't you apply it in the DC circuit? Because application of this thing in the AC circuit is more complicated than DC circuit. For example, if we have an equation with 4 loops, if we have a resistive network with 4 loops, then if you want to solve for the loop current, how many loop currents will be there?
4 loop currents.
If you have 4 loop current, then how many equations you need to solve?
4 equations.
How many times you have to apply your Kirchhoff's voltage law? You have to apply your Kirchhoff's voltage law in each of your loops. As a result, what will happen? You will be obtaining a simultaneous equation that will involve the loop currents I1 through I4. Then you will have an equation that has 4 variables, 4 unknowns there. That means you will have 4 simultaneous equations to be solved. Can you solve it so easily by using your calculator or matrix inversion or by using Cramer's rule? Because in your Cramer's rule, you will have to solve the determinant of a square matrix of 4 by 4 dimension. That is not that easy to be solved by using HAL calculator, okay? Although the problem is very simple. For this reason, actually, direct method is sometimes not adequate for solving a system with huge numbers of equations. But if you have some other technique available with us, like Gauss elimination, you can handle them, no problem. You gradually convert your matrix into a upper triangular one, use your backward substitution. Okay, in some cases, if you need your rearranging or pivoting, you can apply pivoting, but elimination will help you to solve your problem easily. So in this, we'll set some problem from our book. Okay, this example that follows is a mechanical example. You can have a loop there, but we don't have need this thing. We will apply this thing to our electrical engineering network. Okay. Now the thing is that if we have our system that might have complex number, for example, in the case of AC circuit, you will have impedance values are there or admittance values are there, that is are in general complex. That in that case, what you can do, you can split your equation in such a way that you can split into real and imaginary part. You can proceed with handling the system separately by using real and imaginary part. But nowadays, your computer can handle complex number, then we can proceed with complex calculation as well. Now we have your linear system. Okay, this is although we will not discuss the thing that much here, but the essence of the technique should be introduced. The reason is that this technique is usually used in power system. You have already have some introduction with this thing. Actually, the thing is that what? If we usually represent our simultaneous equation in this form in general. Why? Because we have our system equation that we have written in this way. 1, 2. Okay, can we write this equation in this way? A11 into x1 plus A12 x2 plus A13 x3 minus B1 equal to 0. Can we write this?
Yes, sir.
If we can write this, is it not a function of x1, x2 and x3?
Yes.
And that is equal to 0. This is what your first equation. This is what that equation. Okay. If we have a number, you can call it the equation 1, put a subscript there 1. If we have equation 2, put a subscript there x1, x2, x3 equal to 0. Another equation there f3, x1, x2, x3 equal to 0. So in this way, you can write your equation in the general form. This is what this thing. Okay. Now the thing is that how to proceed with solution. If we want to solve with this equation, we can easily use, for example, multidimensional Newton-Raphson method to solve this equation if Gaussian elimination or other technique will not be directly applicable there. Or we can linearize our system by using Taylor series. For example, say when we will be obtaining the solution, in this case, what will happen? No direct solution will be available. For this reason, what you can do, you can start with a guess, for example, say ith guess. Say we have a variable there, say 1. For example, x1 with ith iterative value. Similarly, x2 with ith iterative value. In the same way, you can go to n variable xn with ith iterative value. Okay. So with this value given to us, if we put this value there in our equation, if this equation is correctly satisfied, then xi's are what? The root of this equation are the root of this equation, are not they?
Yes, sir.
If they are the root of this equation, then you can stop. But unfortunately, your guess cannot be such that at the first stage this will be concise. Then how do you need them? You will iterate the solution. Okay, that means repeat your solution. How? You have to find another next iterative value, say I1 into I plus 1. Or in general, you can write that we have a kth variable with iterative value I1 initially present. Now we need to determine another value ki plus 1. That ki plus 1 will be a better estimate than your ki. Then what will happen? There will be difference between these two. Ki plus 1 minus xki. Say this is equal to say h. Then what we can do? We can approximate the function value at x ki plus 1 with the help of the value xk I minus 1 and with some other derivative present there, like your Taylor series that you have already learned in your earlier chapters. That approximation will help us when gradually your slope gradually become 0 and eventually these two estimate will be coming closer to each other, then you will be obtaining the solution. Okay, that particular thing has been generalized in this way. Equation 9.32 is the thing that I have discussed. This is nothing but multivariable type Taylor series. You see that if we have a single variable, only one term will be present. Okay, this is how if we just higher derivative terms are neglected, only first derivative, that is the linear approximation of your Taylor series. Okay, if a single variable is there, then these three terms only exist. For the next variable, this term appears. For the next variable, this term appears. Okay, in this case, what will happen? Your f value will be known to you, and your x value, previous iterative, will known to you. Derivative at the previous point will also be known to you. And if this is equal to 0, that means your next value I plus 1 is the solution of your system of equations. Now the question is that just we have to set this side equal to 0, and we have to solve for xk I plus 1. For k equal to 1, the first variable, k equal to 2 for the second variable, and so on. Then this equation is rearranged in a form something like this. Okay, we can easily write this equation in this form. We will have a metric because each of the term is the multiplication of the derivative with another element. That means we are multiplying a metric. That matrix has the element that is equal to the derivative of our partial derivative of our equations with respect to the variable present there. If we arrange them in the matrix form, it will take the form of a matrix. We call it Jacobian of the Jacobian matrix that you have already learned in your power system. So your Jacobian matrix will be there, that is represented by say Z. Then your X equation, because Jacobians are multiplied by 2 factors. One Jacobians are multiplied by what factor? This factor. Okay, xi1, xi2. In this case, x will be a column vector and xi plus 1 will also be a column vector. Then your equation can be put into this form, that you z into xi plus 1 would be equal to minus xi plus z. And this equation, what is our objective? We have to solve for xi plus 1, but that solution we can use by, once these equations are available with us, then we can use Gauss. It is a matrix equation. Then no nonlinearity is there. Then we can apply our Gaussian elimination technique to solve this thing. But this will be illustrated later with an example. Then another variant of our Gaussian elimination technique is called Gauss-Jordan method. In Gauss-Jordan method, I hope you used this thing in your matrix inversion or in your earlier courses of linear algebra. Here you see that what is the difference between this technique and the naive Gauss. The technique is very simple, right? Okay, here in this case, other than converting our system of equation into a form of upper triangular matrix, it is now converted into a unitary matrix with one value at the diagonals and no other values are there. It is a diagonal matrix with value equal to 1 in the diagonal. Okay, so how can we proceed with it? The algorithm is very simple. If we have our equation with us, we have to augment our original coefficient matrix by the column matrix B. This is the original matrix, and it is being it is augmented by B matrix. Then what you need to do, you use your elimination technique there by row column operations. Then what will happen, you will be converting, for example, a matrix into this form. Then the new B column that you are obtaining is the solution of your problem. Because your equation then now be converted into this form, then directly your new B coefficient will be the solution of your problem. The same problem that is solved by using Nate Gauss is also solved by using Gauss-Jordan. Then you can have a look there. Okay, this technique is very simple. Simple elementary row and column operations. Multiply by some factor, then subtract and gradually eliminate the variable. You retain the coefficient equal to 1, 1, 1 in the diagonal of your matrix. Then the column matrix at the position of the augmented column will be the solution of your problem. Now I will be discussing about another. These are the semi-direct type technique. But if we want to obtain a solution by using some iterative technique, I will just show this technique to you, and you have already learned this technique by using your an iterative technique that we usually use in a method that we call Gauss-Seidel method. You have already have some introduction of Gauss-Seidel method, isn't it?
Yes, sir.
Okay, then I hope you can fairly remember the method. Okay, let me talk about it by using this thing. Okay, if we have our we have two variant of iterative type technique. One we call Gauss-Seidel method, another is simple Jacobi method. Okay. So here what we can do in your Gauss-Seidel method, what we usually do, if we have an equation A11 x1 plus A12 x2 plus A13 x3 is equal to say B1. We can rearrange this equation in this way. We can rearrange this equation in this way that x1 is equal to minus A12 divided by A11 x2 minus A13 divided by A11 x3 plus B1 divided by what?
A11.
Then we have another equation there, A21 x1 plus A22 x2 plus A23 x3 is equal to B2. Then we can rearrange the equation, solve for x2. x2 is equal to what? Minus A21 divided by A22 x1 minus A23 divided by A22 x3 plus B2 divided by A22. Is it okay?
Yes, sir.
Then our third equation is A31 x1 plus A32 x2 plus A33 x3 is equal to B3. Then our we solve for x3. x3 is equal to minus A31 divided by A33 x1 minus A32 divided by A33 x2 plus B3 divided by A33. Okay. Let's say this set of new equations that we are obtaining. So this is 1, this is 2, this is 3. These are the actually iterative type equation in the sense that you can write this equation in this way that you can start with an initial case, then you can proceed with the solution. Your initial case can be 0. Let us consider that our initial case is x1 0, x2 0, x3 0. Then your next step is what? We have to find x1 1, x1 2, x2 1, and x3 1, isn't it?
Yes, sir.
So in finding, for example, x1 1, you have to use this equation. In this case, your x0 value is known to you, your y0 value is known to you, isn't it?
Yes, sir.
So this is your first iteration. And if you want to calculate x2 1 from this equation, your x3 value is 0. How about x1?
It will be x1 1.
X1 1. Okay, if we use x1 1, then we call it what? Gauss-Seidel method. Okay, and if we use x1 0 there in this second equation, that means we are not updating our equation subsequent solution immediately that is available with us. Then what is the name of this technique then? If we do not use, for example, the immediately available value there, it is called Jacobi method. Okay,
Okay, sir.
that means in the Jacobi method, you Jacobi use, for example, not use the immediately calculated value, but the original value. That means in the Jacobi case, we are just considering it. Say this is your GS. This is your GS. If we want to use Jacobi, for example, for x2 1, then in the case of Jacobi, other than x0, we have to use, for example, x0 there. Okay, this will be y0. Similarly, in the case of your GS for x3 1, we have to use x1 there and x1 there, isn't it?
Yes,
And
sir.
that x3 0 will be there. But in the case of Jacobi, it will be 0. It will also be
0.
0 or no, nothing is there. Okay, in this way you can proceed. Then after one run of calculation, you can just, after having your next, let us concentrate with Gauss-Seidel, okay, not Jacobi. You understand the difference between Jacobi and Gauss-Seidel, I hope.
Yes, sir.
So this is your one. Now your next cycle, next values are available with you. Okay, so you do not need, for example, these values there. Then you can use these values. So in this way, what you can do, you can proceed with your ith iteration. For example, you can generalize this equation in this way. Okay, for example, say this is I plus 1th iteration. In this case, what is the value of your variable there, unknown there?
Sir, I have, sir. 2ti.
It will be equal to
So x2i, x3i.
isn't it?
Yes, sir.
Now this I plus 1 would be equal to, this will be equal to I plus 1.
And this will be
This
I.
is
I.
This is I that we have calculated, isn't it? And that equal to I plus 1 would be equal to, this is I plus 1. This would also be equal to I plus
1.
1. So in this way, we can find our iterative algorithm there. Then how to stop? If we want to stop the solution, then we have to stop at this point, that if for a kth variable, I plus 1th iterative value minus kth variable with ith iterative value, take this difference. And if that difference is less than equal to a stopping criterion, then we can stop the calculation. Okay, you can have your absolute something there, or you can calculate, for example, a relative value in terms of percentage.
স্যার একটা কোশ্চেন ছিল, আমাদের কি তিনটা এক্স এর ভ্যালুই স্যার ইএস কে স্যাটিসফাই করতে হবে, রাইট স্যার?
হ্যাঁ,
আমাদের কি স্যার তিনটা এক্স এর ভ্যালু মানে x1 x2 x3 তিনটার এরর?
every value should be compared.
ওকে স্যার, ওকে স্যার।
Otherwise, you cannot have a separate criterion. Just 1 minute, one guy phone. People are actually phoned in a wrong time. Okay, now we have another issue of what we call accelerating the convergence. Okay, in this way, if we proceed, then actually sometimes you will see that your value it will take longer time to converge. Okay, if possible, I will show you. This is very complicated dealing with this book. Okay, you see that if you want to attain this criteria, in terms of percentage, it will be equal to k I plus 1. Okay, you may have you need, for example, many iterations. So in order to just accelerate the iteration, you know that we can, I hope you used it in your power system problem. Other than using, for example, xi, directly there, that we calculated in the ith iteration, we may call it, say, xi new. That should be modified in this way, that xi new would be equal to a factor lambda into xi new plus 1 minus lambda into xi old. Xi old. That means in the ith iteration, we have a value that we just want to call it a new value that we want to calculate. Then that new value can be used, for example, to update in the subsequent calculation. We can use this value. Okay, and that factor lambda is called acceleration factor. And if the value of lambda equal to 1, you see that that will not change the value. The same value will be used. That simple technique. And if your value is lambda is usually the value of lambda will be between 0 to 2. Then if your lambda value is less than 1, then that means between 0 to 1, we call it under relaxation. And if your value is between 1 to 2, it is called over relaxation. And over relaxation is made in successive calculation. For this reason, this technique is called successive over relaxation. Successive over relaxation, or SOR technique. I will show you this SOR with some example later. Okay, SOR is very important. It is problem dependent. If we have a problem, for example, power system, that power system problem can give us a solution quickly with a factor. That factor is actually determined by solving many problems of this type. For this reason, when we solve a problem of practical interest, then this accelerated factor will be given. And some other technique is available in higher numerical technique. By using some spectral technique, we can also estimate the value of lambda, but this is beyond the discussion here in this elementary level. So with this thing, let us conclude our discussion on simultaneous solution. First part, we have our second part there that involves what we call other matrix operation. Okay, have you heard about ALU decomposition in your linear algebra?
No, sir.
No, LU decomposition, that means a matrix can be decomposed into a upper triangular and a lower triangular.
Yes, sir.
But
Yes,
I-
sir.
Sir, we
Yes.
learned it as QR decomposition.
Yes, what decomposition?
Sir, QR decomposition.
In that decomposition, what was the result?
Sir, a matrix was separated into two matrices. I mean, it was decomposed.
Why we need this? What is the utility of that decomposition actually? Okay, no problem. You can have some relationship of the decomposition technique with the decomposition that we are going to discuss inshallah in the next class. That is there in your chapter 10. Okay, try to have a look, because if you can have some previous learning, that will help us to proceed in a faster way. Otherwise, it will take a very longer time, because some of the basic technique is there with you from elementary mathematical technique. You see that how triangulation can be made. Triangulation is nothing but an elimination process, isn't it? You have to successively eliminate the matrix in such a way that it will form a upper triangular, and even we can form a lower triangular also. So later in the next class, I will talk about it. You try to have a look, okay, in chapter 10, how a matrix can be decomposed into two parts, L and U, and can be used to solve our problem of system of algebraic equation. Okay. So with this thing, we'll be concluding our today's lecture. Then we will discuss about how practically we can apply them into our problem. Then we will talk about some special cases, particularly this is applicable for network theory, that we have a certain type of matrix that will cause some special problem. That means in such cases, most of the elements of our matrix will be zero, or your matrix will have some what we call pattern. That means in some cases, only the main diagonal and two other diagonals could be present, and even same pattern can be repeated. And this is visualized. This could be visualized if your system is very large. Such systems with your matrix element, that most of the matrix elements will be zero, is sometimes called a sparse matrix. Have you learned about a sparse matrix or a sparse system? In your power system, this is most relevant, okay? Because power system matrix are always sparse. Okay, that's it for today. You can stop your recording. Inshallah, next day we'll discuss on